Okay, now I didn't really ask people to calculate these forces, and my colors are different here than they were over here. Don't have any fixed color scheme. I've drawn the projections of F applied and F grav onto the delta S vector. Okay, so here are my projections. And again, I repeat, they'd have been the same if my delta S vector would have gone in this direction. My angles would have just been, the angles I use in calculating would just been, complementary to some of the angles or supplementary. Okay. Now we want to calculate, or we want to see if we know all these vectors, then how can we get the perpendicular components of F applied and F grav? Now here I used orange for the perpendicular component of F applied. The component of F applied perpendicular to delta S. It's going to be here. And yellow for the component of F grav perpendicular to delta S. How do we get this vector? How do we get this vector? Well, if we see that this vector added to this vector, well, we'll move this vector over here so its tail is at the head of this one. We see that this vector and this vector add up to the applied force, so that the perpendicular component of the applied force, this vector, there it is just your F applied minus the parallel component of your F applied. That's because, of course, if this plus this equals this, then this equals this minus this. And you can see that directly from the picture too. If you turn this vector around and make it negative, put it at the end of F applied, it comes back here and there's your F perpendicular vector. So in many ways, you need to understand this, and you need to understand the graphical methods of adding and subtracting vectors and multiples of vectors so that you understand this very well. Okay? And then your perpendicular component of F grav can easily be calculated. If you know the parallel component and the F grav, then you just subtract these two vectors and you get this. Now, adding and subtracting vectors, that's not, you can't just add and subtract their magnitudes. Okay, you got to add them and subtract them as vectors. Okay, so anyhow, summary here. Your F applied parallels projection of F applied onto delta S, and your F grav parallel is the projection of F grav on delta S. Then if you subtract the projection from the applied vector, the parallel projection from your applied vector, you get the perpendicular component of the applied vector, and so forth. Okay, now how do we use this in determining things about our other forces? Now, if we know F applied, we can calculate its components, assuming we know the direction of delta S and so forth. And same thing with F grav, we can calculate its components. If this is a box moving along an incline, then the acceleration is only in the direction of the incline. It doesn't accelerate down through the incline, it doesn't levitate up off the incline. In that case, the sum of all your forces perpendicular to your incline until your delta S vector here is going to be 0, which means that your normal force vector added to your gravitational vector component perpendicular to delta S, added to the component of the applied force perpendicular to delta S has to be 0. So that your normal vector is just this. Now, this is an important step. Okay? You have to use Newton's second law. Okay? Applied, in this case, to the perpendicular direction, in which there is 0 acceleration, so that you have 0 force, net force, in the direction perpendicular to motion. So we write